In this video, we're taking a look at one of the more accurate ways to break down your fixed and variable costs, the least squares method. It's a powerful tool that can really improve your decision-making process when it comes to budgeting and forecasting. So stick around because I'll not only show you what it is and how it works, but I'm also going to walk you through a step-by-step example in Excel. Let's get started. This is a simple linear regression equation, and this is what the least squares method for figuring out the cost function actually relies on. Showing it in terms of splitting our costs, we have total cost, mixed, fixed and variable, equal the fixed costs. So those are the costs that are the same regardless of activity volume, plus the variable cost, which is an incremental cost that we have to add every time we add another unit. And when we say activity here, what we mean is, like, for example, production. So those are the costs that we need to make in order for our production facility to run, regardless of whether we produce one item or 500 items. And the variable cost is the specific incremental cost that we have to add for each additional unit of production. Employing some calculus, we can arrive at those two normal equations. And I'm not even going to pretend that I understand it enough to explain it, how we arrive at those. But using those two, we can derive a function for B, which is the variable cost in our function. And once we know B, which only requires the two variables, X and Y, from the observable data set, and this would all make sense in just a second. But as soon as we have B, which is our variable cost, from the equation up here, this is our variable cost, then we can use this B to calculate A. And A uses the means here, so the simple averages, which are those simple equations, which results in this equation for A representing our fixed costs. If you want to plot it, you have the units increasing here and the cost increasing along this axis. This is our fixed cost, which is fixed, so it stays the same regardless of the volume of units. Then you have the variable cost, where you have, for example, for 1 unit, you have 0.5. For 2 units, you have 1, and so on and so forth. So it's incremental with the same step. And once you add those two, you get the total cost, which is Y equals A plus B multiplied by X. Now let's make it make a bit more sense with an Excel example. So what we have here is data for 10 batches, where we have the volume of the units that were produced and the production cost. So these are our X and Y. And N is 10, the number of items of observable pairs that we have. So essentially we have everything to calculate B. We have N, the number of observations, X and Y, our volume of units, and our production cost. But before we get started with that, it makes sense to see if there's even correlation between those two. So can we look for one of them being able to explain the other, essentially? So what we can do is we can calculate the correlation between the two using the correl function. And we're going to grab this as one parameter and this as the other parameter. And you see that correlation is 0.64, and usually between 0.5 and 0.7, we'll say that these are moderately correlated, which is good enough to be able to draw some conclusion from those two. So if we grab those and we plot them on a scatter chart, we get this chart here. So those are all the observable pairs from our data set. We can select the data set here, right click and add trend line. And this is the line we're looking for. This is our Y in the formula of Y equals A plus B multiplied by X. So this is our Y, the total cost that we're looking for. And the least square method essentially looks for the line that minimizes the squares of the distances from all items. So essentially, right here, the error is the distance between those two. So our line is offset from this. So this is an error. And we're looking for the line where those errors for each of those pairs is minimal. And this is where one of the biggest drawbacks of using the least squares regression model lies, is the fact that it's really sensitive to outliers. So if we have something that's way off from the rest, it can skew our analysis because the distances are squared, making their impact much larger. Okay, so now that we have that, let's calculate some supporting functions. So I'm actually gonna move that over here so it's out of the way. And in order to calculate b, we need x multiplied by y, and we need x to the power of 2. We copy that formatting here, and this is where I'm getting those. So let's just bring that formula over here for reference. So x multiplied by y is this multiplied by this. We close that, and then this is x to the power of 2. Format those, copy them down. Then I need total, the sum, and I also need the mean, the average. So the sum will be this. I'm gonna copy that over to the side, and the mean will be average of those here. And I'm also gonna copy that to the side. Both those, because those are the ones that we'll use. And this means that now I can use this formula to calculate b. I say b equals, and here equal bracket bracket, I'm gonna say 10, this here, multiplied by the sum of x multiplied by y, so this thing here, minus the sum of x, which is this thing here, multiplied by the sum of y, which is this thing here. I'm gonna close this bracket, and then I'm gonna do this here. So again, we'll have our 10 here, the number of items, multiplied by the sum of x squared, which is this here, minus the sum of x, this here, to the power of 2. Okay, and we get 36.69. So this is our b, or our variable cost. This is the incremental cost that's added for each additional unit of production. Then for a, we can use the other formula that we had. So this will equal the sum of y, but in brackets, so the sum of y minus b multiplied by the sum of x divided over the number of items, and this is 393,872.47, which means that we can build our function for the total cost. This is my fixed cost, and then my total cost, or y, will be equal to 393,872.47 plus 36.69 multiplied by x, or small x. So this is a cost function that we're trying to figure out, and we can now use that to forecast future batches or additional batches to support our forecasting or decision-making processes. So for example, what happens if we had 16,000 units? So for 16,000 units, we can do A, I'm gonna fix it to F4, plus B, again, fix it to F4, multiplied by our 16,000 units here. So this is the total cost that we get. Then what happens at 16,500? Copy that down, and it's almost 1 million. To quickly recap, there are a few advantages and disadvantages. The major advantage is the simplicity of the least squares model for calculating of the least squares model for the cost function. It's also applicable in pretty much any situation. I'm struggling to think of a case where it will be inapplicable. And also by relying on one of the fundamentals in statistics, the model has a pretty strong underlying theoretical foundation. Then on the negative side, as we already noted, is quite susceptible to outliers, since the distance between the data points and the cost function line, so this distance here, is squared. It also has an inherent assumption that the two variables that we're analyzing, x and y, have at least some kind of correlation. This is why we checked this here and show that these are moderately correlated. And the other thing is that we need the data to be normally distributed. Otherwise, the method might yield unreliable results. But we can almost always mitigate that by just adding more and more data points to our sample. The least squares method is probably one of the most popular predictive analysis techniques in statistics. It's widely used to fit a function, our function down here, to a data set. And we looked at like the basic version of this, where this function represents a straight line, but it can be a curve or even a hypersurface in things like multivariate statistical analysis. So it's a really versatile concept that's applied throughout medicine, biology, finance, agriculture, sociology, and pretty much everywhere where statistics is involved. Now you know how to leverage the least squares method to improve your decision making when it comes to budgeting and forecasting fixed and variable costs. If you want to learn more about financial modeling, I've created an entire beginner financial modeling course that's available absolutely for free right here on YouTube. You can check it out in this playlist up here. Thanks for watching, and I'll see you in the first video.